I'm Public Utilities Director for City of Perrysburg. Welcome to this third public meeting on the Grassy Creek Stormwater Master Plan study. We have here tonight from the City of Perrysburg also Mark Dunsmore, who's Commissioner of Public Utilities, and Lauren Rush, who is Stormwater Program Technician. Our consultants here tonight who will be making presentations, we have Kathleen Smith, who's a professional engineer, is project manager and an associate with Hazen and Sawyer Consultants in Columbus. And she is joined by Chris Richley, who's a project engineer, and also Dustin West, who is an assistant engineer with Hazen and Sawyer. Please be aware that there's recording in progress. We're recording this so that the people who cannot attend will be able to look at this later. And once again, we're happy to see you here tonight and hope to provide a lot of helpful and informative data and information. Kathleen?
Yeah, one housekeeping item is, I know that we tried to catch everybody as you were coming in, but there's a sign-in sheet in the back, so if you could please sign in, we would really appreciate it. All right, so let's go ahead and get started. So this is the agenda for tonight, so we're going to be kind of doing a quick overview in case some people weren't able to make it to meeting 1 and 2. Again, this is going to be a quick high-level overview. Then we're going to be looking at the survey results from the discussions that we had last time. Then Chris is going to take us through the modeling and the existing conditions in the system and looking at a couple of alternatives that we studied. And then we'll go over the results, and then we want to get your feedback. And so there'll be a questionnaire at the end that we'll hand out to you guys, and we'd love for you guys to fill that out and then hand it back in. So a quick overview, we started out this project kind of collecting data from you. So at our first public meeting, we asked you guys where you had experienced flooding in your neighborhood. And we used that information coupled with field data that we collected to generate a computer model. And we talked about that computer model that we generated at the last meeting. So since the time that we developed that computer model, we have been working on alternative analysis, which is looking at improvements. So using that model to look at different improvements and see what happens in the system. And our ultimate goal here is to put together a master plan to give to the City of Perrysburg for their consideration on what to do for the area. So the ultimate goal, again, is we're not going to put shovels to the ground at the end of this project. We're going to recommend a plan to the city to consider. Okay. So from the first public meeting, we gathered a whole bunch of information from you guys. There were lots of complaints, especially regarding backyard flooding. So there was 35 backyard flooding complaints. There was complaints of front yards, general flooding, streets and sidewalks. You see on the table on the side here, we have the street where the complaint was lodged, and then the number of complaints per that street. You can see Maple was kind of the hot spot. Walnut as well, but Maple had 14 complaints. Okay. So this is where those complaints were located. So we took all of the information that was gathered at that first public meeting and put it into our GIS system and kind of located. So if the complaint was that there was a backyard flooding, we put that dot in the backyard. Okay. And so that's what this graphic indicates. So this is where flooding complaints were logged. And again, our project area is kind of bounded on the south end with South Boundary Street, okay? And then the northern boundary of our area is Grassy Creek. So last time we talked about the computer modeling that we did, and these are the results that we looked at last time. So we ran a historical storm over the area, and we kind of correlated those complaints, which look like the little flags, and we correlated those to the flooding depth, which is shown in different shades of blue in the figure. So you can kind of see where there's lots of shades of blue, maybe in the backyards and things like that. that's where the computer model is showing that there's flooding. Yeah.
Are these photos going to be available to us? Can we view them sometime, or is this the only time I'm going to see it?
Well, so the question was, just for the recording, the question was whether this would be available, those pictures. Okay, yep.
It'll be on the city's website. We've already talked to our public information officers, so.
Yep, so it sounds like this is gonna be available, so this presentation will likely be available in a PDF form following this meeting.
If you'd like to have a PDF emailed to you, just get us your email address and we'll send it out to you.
Okay, so last time we talked a bit about alternatives, and so we talked about some strategies of things that could be done in the neighborhood. The first one was bioretention and rain gardens. So these are basically, they're kind of shown, maybe this will work. They're kind of shown here. So they're basically areas where the water would drain to, and they would be filtered through a soil that infiltrates very quickly and into a gravel layer. And then from there, it can be stored a bit until, you know, the under drain can overflow into the storm system, so the water doesn't get too high. But this will basically kind of detain water, slow water, and encourage infiltration into the natural groundwater. Another option is storm sewers, which again, there are storm sewers existing in the area. This would install new storm sewers, which would take that water from basically the right of way and take it to the creek. Detention basins and underground storage, these are just basically locations where the water could be held until a later time and then pumped or discharged to the stream. Backyard drainage, this was an option that we talked about that the city could provide kind of an area drain in the backyard, but this option would require easements from individual homeowners, and the city could locate a storm drain in the backyard and then drain that to a storm sewer in the front yard. We also discussed the sump pump program, which is a program that the city currently has to disconnect sump pumps, which currently connect to the city's sanitary system. And the thought was maybe we could leverage some of that work and couple that with draining the backyards. So when we had this meeting last time, we kind of asked your guys' opinion on what you thought about these different alternatives. And so we gave you guys a questionnaire to fill out, and then I'm gonna kind of summarize the results of that right now. So here are the survey results. So the first question was whether you are in favor of bioretention or rain gardens in the right of way. So this would be from basically maybe the sidewalk to between the sidewalk and the road. So that's the right of way. And it looks like the votes came in about half and half, with maybe just one more vote toward the no, that you guys weren't in favor of rain gardens. So maybe 50-50 split. There were some additional comments. Basically, it said you kind of depend on the location, whether you thought that would be a good idea or not. And, you know, rightly so, one of the comments was you're okay with it as long as the bioretention or rain garden drained into a storm system. And those bioretention or rain garden systems will have to be drained with a storm system. Okay? So we also asked whether you'd be interested in installing a rain garden on your private property. And the results came back, 7 of you said okay, and 10 of you said no. So this was a little bit more swayed toward not putting a rain garden on private property. So it seemed like folks were willing to consider this design, and again, these would be drained to a local storm sewer. The next question was storm infrastructure. So storm infrastructure would be placed in the right-of-way, and it would drain from the front of the house and take it to the creek. So this seemed overwhelmingly, yes, you guys are in favor of installing storm sewers using that technology. So there were 11 votes for yes and maybe 3 votes for no. And the concerns, I think, with the no were with any impacts that would have to the creek. Okay. And cost. Another option was underground storage, where we would take some of the stormwater and store it underground. And that seemed to be in favor as well. There was 8 votes for yes and 6 votes for no. And the concern here, one of the comments said, as long as it's odorless. So that was probably a concern of location and any other odors or things like that. And again, cost was a consideration here. And then backyard drainage. So this one received 10 votes for yes and 4 votes for no, and people seem to be pretty, I guess, on board with this option as well. And again, this is, as shown in the figure here, there's the street in the front, which is depicted at the bottom of the figure, and then the pipe would be installed between the 2 lot lines, and pipes between the lots in the back. And then there'd be a catch basin to try to drain the area in the backyards to the catch basin, and then that would be routed to the street. And then we also talked about the sump pump program, and it didn't seem like we got 0 votes for yes as far as sump pump participation. Some people have already participated. Some people don't know if you have a sump pump, so it seemed to be some questions about this program. So it seemed like there's not a lot of I guess interest at this time for the sump pump program and for participation in that program. So to kind of summarize the feedback that we got from you guys last time, I just counted up the number of yes votes. And so it seemed like storm sewers and backyard drainage were kind of at the top of your guys' list, and then detention and underground storage were next, and then bioretention and rain gardens in the right of way followed, and then private property, rain gardens. Okay, I'm going to turn it over to Chris to talk a little bit about existing conditions and the model alternatives.
Okay, so before we get into looking at any sort of alternative, we need to identify a level of service that basically we want to accomplish the mitigating flooding, not causing any harm to Grassy Creek. And we need to run the existing conditions model for that specific level of service. So we have some kind of comparison. So we develop alternatives, but then we have to compare that to what it is today in order to figure out what the benefit of that is, as well as do not make anything worse than it currently is today. So we identified the 10-year design storm as what rain event we want to use to basically characterize the existing flooding, and then also use that to identify what the level in Grassy Creek is along the entire stretch within our project area. And just to give you an idea, that's roughly 2.8 inches in about 6 hours. So in any given year, it has a 10% probability of having a rainfall that intense with that depth. So it is a rather large storm, and it's a typical design storm that's used in sizing storm infrastructure. Because, say if you wanted to use a larger event, like say you wanted to develop alternatives for a 50-year storm, so more intense, more rainfall storm, you're just going to end up spending more money to reduce that flooding. So it's a matter of, how frequent would a certain rain event occur versus cost. So, you could come up with alternatives for different rain events, and you'll see, the larger rain event you use, you're just going to see it exponentially increase in terms of cost to prevent flooding in that more severe rain event. So it was decided to use a 10-year design storm. And what we wanted to look at was, what do you consider flooding? And so, we ran the model with that 10-year rain event, And then we looked at ponding depths in our model, and we said, you know what? If it ponds like, the first 30 minutes, hour after a rain event, is it a big deal if it slowly infiltrates or slowly works its way into the storm system? Or do we want to consider flooding, something that's more of a nuisance that lasts several hours, days, and use that kind of as our, what is the flooding volume at this point in time? And what we found was we actually ran the model for 8 hours and looked at the flooding volumes. And we also ran the model and looked at, what's the flooding after 24 hours? And basically what we were seeing is it was roughly the same volume. Basically the soils in this area are clay type soils. So, infiltration's really slow. And that's kind of why you see after a rain event, you see ponding. It'll last, depending on where you are and how close it is to the storm system, it could last days, weeks. But the infiltration in this area is very slow. So not having infrastructure at some of these depression areas, you're going to have ponding, and it is going to last for magnitude of hours, days. In talking with some other people, weeks. So and not only do we want to look at flooding, but anytime you look at alternatives that are going to basically reduce flooding, basically that's going to be getting in the storm system and eventually Grassy Creek. So anytime you take water that's just ponding and you send it to the creek, it's going to increase levels in the creek, and it's also going to increase peak flows. And we do not want to increase peak flows because when you have higher flows in the creek, you're going to have higher velocities. You can scour the banks of the creek. We basically want to maintain the creek as it is today. We don't want to send any more peak flows to the creek, and we don't want to cause any increase in depth with taking the flooding from the lawns and backyards and putting it to the creek. So what you'll see is we'll show you plots along the entire Grassy Creek that compares the levels in the creek and the flows in the creek, what they are today compared to what they are when we run our alternative model. And then, of course, you also want to look at what's the capacity of the existing storm sewer. Are there any undersized sewers that cause some of this flooding? Or if you're taking flooding from the yards and taking it to a sewer, does that sewer even have the capacity, or are you going to have to install new sewers? So that's some of the stuff that we looked into. And just to kind of, I know we mentioned this at the last meeting, but for people that weren't here, so our model basically, it's a model of the storm sewer network. So it's got all the inlets and pipes, but it also has the surface, and we used a detailed elevation map that basically has point elevations in 2.5 foot grids. So it's very detailed. And in the model, there's different surface cells that all kind of match up in a line, and each cell has an elevation. And so what we do is when we look at where the flooding occurs, we look at each individual cell. And so this map is an example. So if we run a 10-year rainfall event, so that 2.78 inches over 6 hours, and we can, after 8 hours of that rainfall event, we can look at what cells are flooding. So any of these blue cells in the map are, 40 foot by 40 foot cells that have ponding surface water after 8 hours. So it has not drained after 8 hours. And so the lighter blue cells are cells that range in depth between 1 and 8. And that's typically what you see throughout the planning area. However, there are localized areas where you see as much as 16 inches of ponded water 8 hours after the rainfall event. And a lot of these occur, as Kathleen mentioned, in the backyards or in the right-of-way between the street and around the sidewalk area. So when we say we're trying to address flooding, we're looking at these cells and trying to basically take this ponded water and get it to the storm system and eventually Grassy Creek. So this is a map showing the flooding under today's conditions, not doing any changes to the system. And what we tried to do is any contiguous set of cells, so any cells that are bordering and they both show flooding, we combined them into one area. And this map shows all the different polygons that are, range from red to blue, are all different flood areas within the service area. And what we tried to do was prioritize them in terms of flood volume. So anything in red has a flood volume of 400,000 gallons, all the way down to blue, which is around 1,500 gallons of flooded volume. So as you work your way to the blue, it's just more kind of localized, just smaller depressions with ponded water, whereas the red, orange, and yellow are kind of larger areas where, maybe there might be opportunities for more cost-effective solutions. But
With these questions, with your exploration, is that due off of theory or is that due off of what actually we had? Are these from observations?
Yeah,
physical observations, pictures and all?
Good question. So the question was, does this figure show flooding that was actually measured out in the field, or is this theoretical values from the model? And these are basically the results from the model. So what we did, just to kind of backtrack, is so we first developed the model, and then what we did was, so we had over 50, 60 complaint points from the first public meeting. And then also as part of this project, we actually had a wet weather response team. So what we did was, I think it was four or five different rain events. We had field crews go out there and basically take photos of all the ponded areas so we could have the extents of the flooding and kind of estimate the magnitude of the flooding during those specific rain events. And then they also measured levels in Grassy Creek. And then what we did was, so we actually ran the model for that rainfall. So the city has a rain gauge out in the system. And so we ran the model with the rain gauge, the Perrysburg rain gauge. And what we did was we looked at the model results and we compared them to all our field photos. So we said, we looked at the extents of the ponding, like how much spread did it have, and we tried to estimate the depth the best we could, and kind of use our model to validate it. And say you had a location out in the field that you took a picture, and we look at our model and say, you know what, it's not matching up the best. So what we do is you kind of what we call validate the model. So we can say, you know what, maybe this parameter that we're using in this set of cells, it's not matching what we're seeing out in the field. So you adjust values based on what you see. This is what's typically done in any sort of modeling is, you have some kind of monitoring data or field investigation data, and you have to basically adjust certain parameters within engineering standards. So it is the realistic values, but you're adjusting them based on site-specific observations.
And maybe I went over that too quick, but we talked about that last time we were here, where we had the model and we had the historical storms, and we went over that to show that we were predicting the modeling that was observed in the field with the model.
And then after we took the field data that we collected and used it to try to best validate our model, what we did was, so we had complaint data and we geocoded it. So basically we had maps up front. And so we talked to people and we put a sticker on the location of the flooding, and we also documented, what type of flooding, what's the frequency, so how often does it occur? Sometimes it's hard to remember, you had flooding, in the spring of 2018, but it's hard to recall the specific date. So we did the best we could with running. If you said, this happens every summer, then we modeled our model with like a 1-year rainfall event. So, kind of the largest rainfall event you would see in any given year. And we tried to use that to match it up. We're showing flooding here. Was there a complaint here? So we tried that's I guess the best practice to try to validate, what you're seeing from the model versus what's actually happening.
question I had, if you took comments from those who were here.
Correct.
I unfortunately was ill and I couldn't make 2 meetings, and I'm finally here. My question is, when I saw that first map with the points of complaint, I'm like, whoa, our whole neighborhood doesn't even have a point in it, and we were solid underwater for 2 months. I mean, you know, I'm like, whoa, did you not, I had
Right.
phone complaints, did they not get turned in, or they not, they're not there?
Yeah, so we did get complaints via email, and I believe Kathleen spoke to a few people over the phone, and we did get additional pictures. So just because, I just want to point out, just because there wasn't a flooding complaint documented, what we got from you guys.
You physically got there and looked at it, though. Because I asked people to come out, I said, come out. I mean, you're talking 2 months of being underwater in your backyard is a long time to be underwater.
Okay. Yeah, and I guess, so, you know, what we're seeing from the model is there is more flooding observed through the model than what the complaint data that we do have. So, you know, maybe it's something where if you have time after the meeting, maybe we want to make sure we document, you know, where you live and take a look at what we're seeing in the model just to make sure. I think that would be the best approach, but yeah.
And this sort of relates to this question. My question is, how does the model flooding correlate to the complaints?
It matched very well. So essentially, what we did was, and I think it was on one of the initial slides that Kathleen presented, but it was a map with the blue bubbles. So we took those complaints and basically geocoded them, and we placed them the best we could. So if you know, the complaint was, I have backyard flooding, and from the meeting we had a sticker for the address. We placed that bubble on the backyard, and you know, whether it's, you know, this side of the backyard or this side of the backyard, what we did was we just put the point in the backyard, and then we compared our flooded cells versus that complaint point.
Well, I guess looking at that, you can correct me if I'm wrong, but wasn't Maple Street the one that had the most complaints?
Yeah.
Well, I don't really see that reflected here, that you would expect a lot of flooding.
Well, yeah, I guess
Well, Maple and Locust
it's
butt together, and so, yeah, there is, between Maple and Locust, though, there is a lot of color, and that's where there was a lot of.
Correct.
Is this the pointer?
There's a pointer right there, yeah.
Between.
So right,
between
yeah. So this is Locust and Maple. So you've got all this backyard flooding.
Yeah,
Yeah.
Just to clarify, because we did miss the earlier meetings, but, so why is Grassy Creek a boundary? It receives water from both sides.
Correct. Oh, and that's a good point. So what you're seeing, the boundary here is the actual study area where we're going to be looking at flood mitigation alternatives. But in our actual model, our boundary actually, so we are actually modeling the north side of the creek. So we are representing any rain that hits the surface and actually is either piped or drains to Grassy Creek. That is in our model. We're just not.
Not those that sit in our yards, on that side of Grassy Creek. So, you know, that's something, there's significant flooding on the middle part of Mulberry Street, just outside the boundary.
Right.
And there are no drains there. There's no stormwater drains except for on Finley or at the far end of Mulberry and west south boundary.
Right, understood. Yeah, just the scope of our work was to develop a master plan for this boundary. So, you know, I understand you have flooding. Our intent was to concentrate the focus on the flooding south of the creek,
Yeah,
but as well as what's occurring in the creek as far as levels and peak flow, and not trying to, you know, so what we did is when you develop a really detailed stormwater model, so we have thousands of surface cells in the model. So it actually, so when we hit the model run, it takes about, 2 hours to run like a 24-hour simulation. So what we have to do is, since this black boundary is our study area boundary, we developed this detailed surface mesh, basically anything south of the creek. And what we did north of the creek is we have kind of typical model catchments that's typically used is where you have kind of just boundaries. So this area drains to this point, which drains to this point, and you basically assign, one surface value. So what's the roughness of the surface? What's the slope, the area, percent impervious? But we're not physically modeling like the ponded water on the north side, unfortunately.
I get it, it's outside of the project scope, however, you did account for the flow that contributes from that area when you model
Right,
Correct.
the creek elevation to the
right. Yeah, and so basically when you're modeling with this, like, I guess, lesser resolution model, so that our area north of the creek, basically we have to make adjustments to those large, like weighted average. So basically you have a weighted average value for all the hydrology parameters, like, how much of the area is impervious, what's the average slope, and there's one value that's ponded water depth. So it's basically like how much does the water have to build off before the actual runoff from this area actually physically drains. And so we have to do our best and come up with a weighted average value for that area. How much will it pond before it gets to the creek? And I guess the best information that we have is going out there in the field during these wet weather events and try our best to match up with what we're seeing. Unfortunately, I feel bad I can't address your question further, but so okay. So then, looking at the existing conditions model, what we'll also be looking at, so the top graph is basically the peak flow as you're going along Grassy Creek from west boundary to east boundary. So, and you can see, obviously, you see an increase in peak flow in the stream right around Elm Avenue, and that's where the largest storm pipe in this area discharges to the creek. And then, so what we're going to want to do is when we're running our alternatives, we'll plot this peak flow in the existing conditions along the creek, and we'll compare that to the alternative models of calculated peak flow along the creek. And I guess the goal is to not increase the peak flow.
Is that millions of gallons per day?
Yep. So that's in MGD, million gallons per day. The bottom graph is looking at what's the maximum water surface elevation in the creek at that point of the profile. And this is, again, existing conditions. And then the dash line is what is the current riverbank at that same point. And so what this riverbank elevation is the survey. So we had a surveyor survey cross sections throughout Grassy Creek. I think they got 40 or
I think close to 80 cross sections.
80. And what the bank is considered is kind of the inflection point of the creek. So, normal flows would be within the bank of the creek. So there are portions of the creek in a 10-year event that actually go above that inflection point. And again, if it goes over the bank, doesn't mean it's spilling out into people's homes. It could, but what we're finding it does not. And what we did was, not only did we look at the profile and compare it to the existing condition profile, but we also looked at the model and looked at the extents of the flooding beyond the creek boundary. And the goal of the alternatives is, not prevent the creek from flooding. What it's trying to do is, when we're looking at mitigating flooding within the project boundary, we don't want to make the creek worse. So by sending additional flow from these flooded areas to the creek, we don't want to cause an increase in depth or peak flow compared to what our existing condition model is doing. Does that make sense? So, again, this is for a 10-year rain event. So we're comparing the existing conditions, 10-year high level versus our alternative high level.
Chris?
Yep.
Is this the 8 hours after the event or
No,
what?
so this when we look at the creek, what we do is we look at peak. So we look at the entire duration of the model simulation and what is the peak level at any point during the rain event and after the rain event.
Yeah, so in the chart, it could be, that's the peak, that blue line is the peak, and so it could be there for, 5 minutes, or it could be there, I mean, it's the highest point that was observed in the model, and that's what was plotted on that blue line.
So, and then again, before we get into the alternatives, what we also looked at was existing capacity of the storm system. So we looked at, when we run this 10-year design storm, what percent full are these pipes? So are they at capacity, or are we going to be able to send more flow to them? So what you can see is, roughly 80 to 90% of the storm sewers are greater than 90% full. And again, this is a 10-year event. And you can see basically a majority of the pipes are between 80 and 100% full, so they're either red or orange. And at first you would think, hey, all of our storm pipes are undersized, but that's not necessarily the case, because again, storm sewers are designed to basically, for a certain level of service, how much storm flow do we want to convey, and how much can we live with, ponding in the street and eventually getting into the creek. And again, it comes down to, how much ponding can you live with in the street versus how much money do you want to spend. You could put in way oversized pipes and, have plenty of capacity, but at what cost? And another thing is too, so we plotted the manholes in different colors, and basically they're color coded. They're the circles. They're color coded based on what is the maximum depth from basically the top of the manhole to the max level, surface level in that 10-year event. So even though some of the pipes are surcharged, the level is not getting up to the street. So you see less and less red. You basically have, a couple feet of freeboard. So you're basically surcharging your sewers, but in most cases you're not actually getting to the top of the manhole.
So for example, along Elm Street has a couple pipes that are red. That basically means that the pipe is pretty full. And when Chris was talking about surcharging is when the pipe is full and it can start to go up into the manhole area. But you can see on Elm Street, the manholes there are green or blue, which means it's not getting up to the top of the manhole. So you still have a lot of room inside that manhole. So you're maybe getting your pipe full, which is what you want to use. You want to use your infrastructure, but you're not getting close to like overtopping your manhole and getting into the street.
The Locust Street there, close to the south boundary, that is a creek, which sits on the west side of the
Correct.
street.
Correct.
So anything on the east side of that street has no access. Well, you have access, but you got to go underground.
Yep.
To get there. So
Correct.
It looks like there's a sewer there. There isn't. That's a creek.
Correct.
That,
Yeah.
That ain't no off into something else.
Yep.
There's no storm sewers out there.
There's it's a swell on the east side of Meyer Field. Yep.
On the west side of Locust, which is where I'm at. It's across the street from it. So we have no access to that drainage at all.
Right. So you're talking about
On Locust
right
Street,
here, right?
yeah, right there.
Yep.
That red line there is a creek on the west side of this road.
Yep. So this is that little creek or swale.
Little ditch.
There's a catch basin.
Locust and Maple Street, in between there, we don't have access. That's the problem. We've got no access to the water going anywhere.
Into this swale right here.
To the ditch.
Yep.
Well, you're up further. I'm talking close to the south boundary there. That's the general idea. That creek is on the opposite side of the road.
Oh, right, yep.
All the red lines are depicting storm sewer?
Yes.
That's not a storm
There's no
sewer.
storm sewer on Maple Street.
That's-
There is no storm sewer on Maple Street.
We have no storm sewers.
There's no storm on that.
And the reason for that is because of the size of the property that was told a long time ago. Those streets will never have storm sewers simply because it's based on your square footage. And because our lots are so deep, that we'd never be able to afford it. So we have combination sewers in the sanitary sewer.
Okay.
Tile water goes into the sanitary sewer. Not runoff water, but tile water
Okay.
goes into the sanitary.
Okay. Yeah, so all the storm infrastructure in our model was basically surveyed. So maybe I goofed when I made this figure and I added in that. Do you recall that, Dustin, on Maple?
On Maple, that was surveyed. So there is an infrastructure on there. They're not open lids, they're closed lids. So it's not necessarily indicating that stormwater would get into the pipe. That is the pipe down at a surveyed blackness.
We have a front yard sanitary sewer run. The sanitary sewer line runs down our side of the road, the creek is on the opposite side, on Locust Street. And it's a combination sewer, what they call a combination sewer.
Okay.
We're 50-some years there, so yeah, I remember that very distinctly, what we have and what we don't have. I was told we did not have storm sewers.
Okay, we'll take a look at that. But we were basing, so when we built the model, we used a combination of storm sewer atlas maps, the city's GIS, and field surveys. So we'll have to take a look at that.
Mulberry's not separated either. So that's still combined.
On the south side.
I'm pretty sure it was not part of the phase separation.
Okay. Is
That's
that-
correct. There was no separation south of the creek. Because the map showed no combined sewer south of the creek. But
There's no active catch basins that go into the sanitary. Maybe sump pumps from individual houses that act as a combined sewers, but there's no catch basins that are dedicated. to
It's interesting, because if you look at the Locust Street again, there's it dead end, I mean, there's nothing there. The creek is still there, but what they did was the homeowners put the line through and then covered over it, so you're showing it as having no red line at all, and all of a sudden there's one dot, and then there's a little longer line, but that's all open creek. As an example, but where it doesn't show, there is a line that runs underneath there, but that's because they,
Is that with the gravel, the little gravel? Is that the gravel?
yeah,
Okay.
something like that.
Yeah. Okay.
The creek, is that just colored blue because it's the creek or?
Yeah.
Okay.
Yep. Yeah, so this is just looking at the capacity of the existing storm infrastructure.
Okay.
Is there another question?
Mhm.
If you were saying you could have run the 50-year storm,
Mm-hmm.
if you ran the 50-year storm, they'd all be red.
Yeah. In any utility system, it would be
Right.
red, yeah.
If you ran the 5-year storm, would you find that we're better off by facing the worst storms that kind of average every 5 years?
Yeah, definitely. I mean, if you run the 5-year event, you'll have more available capacity in the sewers. It's just what level of service do you want to, it's going to cost more to mitigate, 10-year flooding than 5-year, and it's kind of, how much of flooding can you live with versus the cost. And so, something, as we're developing a plan, you can look at, a cost curve. So, if you came up with a recommendation to address 10-year flooding versus 5-year flooding, what you'll see is, so you plot, the level of service versus cost, and you'll kind of see a curve, and there'll be a knee of the curve, which is basically the inflection point, where if you do anything to fix flooding beyond that inflection point, your costs are going to go up a lot for the amount of reduction in flooding is going to decrease as costs dramatically go up. So you try to find that inflection point. Where does it become not as economical to try to address that flooding?
Another question.
Yep.
Just out of ignorance, I don't know much about these things, but when were these storm sewers put in, and how long is the life of a storm sewer? Were these things starting to be deteriorating at any point?
They were put in when they built the roads, the majority of them. Are they in good shape? They're not in good shape.
I'm sorry?
They are not in good shape.
Not in good shape.
Correct.
Yeah, so I mean, typically, I guess the rule of thumb for say a sanitary sewer is generally around 100 years. Again, it really depends on the characteristics of the drainage area, location of the pipe. If storm, on the other hand, is kind of less uncertain because utilities are more apt to inspect their sanitary sewers, because there's, obvious complaints that people have with odors, or, if a sewer breaks, you're probably in a little bit worse position than say a storm, because the water's going to drain somewhere. But I would still roughly put it in the ballpark of 100 years. And I guess
That's new construction stuff, not the stuff like clay pipes we're talking about.
correct.
Right.
No, see, and that again, it comes down to pipe material, where it's located, condition, installation. But what some utilities do is, so they'll CCTV their pipes, and there's like a coding system. It's called PACP, and basically there's nationalized standard codes for different defects in pipes and different scores for each type of defect. And so they'll video a pipe and they'll document the defects along the pipe and eventually assign a score to that pipe. And the higher the score, the higher criticality it is that, hey, we probably want to go out there and fix that. So, a lot of times you'll inspect pipes and you'll give scores, and, you can make that determination. Do we put in a new storm sewer to replace that aging pipe as part of the alternative, or do we put in a parallel smaller pipe? There's a lot of different factors you look at.
That assessment's been done? Is it?
Probably not on the storm.
No, it hasn't.
Just in general, usually sanitary sewers are more of the focus on the inspections are sanitary sewers. It's pretty typical with most utilities.
All right, we have maybe 15 minutes left in the formal presentation time, so can we kind of pause on questions till the end, please?
So then getting into the alternatives. So what we try to do is we tried to break up the alternatives into, first, if we just address flooding in the right of way. And so the first thing we looked at was, if we put in new storm inlets and new storm sewers or upsize existing storm sewers, what would be the impacts on Grassy Creek of that and to the overall flooding in the area. So basically the green lines in this map are where we located storm infrastructure. The red shapes are the flooding that remains. As Kathleen noted before, a majority of the flooding in this area are backyards. So these storm sewers and inlets along these streets can reduce the system flooding, surface flooding, from 3.28 million gallons down to 2.6 million gallons. And again, we're just focusing on the right-of-way with this first scenario. So when we start looking at, okay, when we're sending this additional flow to Grassy Creek, what are we doing to the creek? So again, this top profile is the peak flow along Grassy Creek from west boundary on the left to east boundary on the right. So the blue line is, again, existing conditions, peak flow. the dashed orange line is the peak flow from our alternative. So you can see towards, Elm Street on, we're increasing the peak flow in the creek. And then in the plot, we're also, on the bottom, we're also increasing the surface elevation because we're sending more flow to the creek. So we're actually increasing the peak flow from 90.95 MGD up to 93.08. So we're increasing it by 2%. The max water surface elevation in the creek, we're increasing 0.09 feet, or roughly a little over an inch. However, we're reducing the system-wide flood volume by 20.7%. So basically, we're reducing the flooding in the right-of-way. However, we're still increasing the stream elevations and flow, so we're not meeting our level of service goal here. And you might have sticker shock, but if new inlets and storm infrastructure were installed to reduce that right-of-way flooding, it's estimated that it will take $1.8 million. So what you're going to see is, resolving the system-wide flooding is not a cheap scenario. And as we go through the alternatives, those costs will just keep going up. So still focusing on the right-of-way flooding. So what if we have those new storm sewers and inlets in the model, but we include storage to basically reduce peak flows in the creek and peak depths in the creek? So we did look at opportunities for shallower regional storage, but what we were finding is due to elevation, there's not a lot of grade change. It's going to be very difficult to get a lot of useful storage out of that and be able to drain it back to the creek. So we focused on underground storage, which you can provide more volume. So you can basically take more flow volume off the storm system before it goes into Grassy Creek, and you can hold it back and store it, pump it back to the creek when the levels are going down. So we wouldn't increase peak flows or depths in the creek. So we focused on opportunities on city property. So the first option is we looked at a tank located just north of Municipal Park, or the municipal pool. We also looked at east of Meyer Field, and also north of Mr. Freeze, east of Eisenhower Park. And again, sizing comes down to a cost. The deeper the tank, the more pumping you're going to have to do, which is, more higher costs. But we also want to, stay within a reasonable footprint as well. So we decided to go with 0.5 million gallon tanks. So in the scenario where we're addressing right-of-way flooding, where we're putting in new storm inlets, new storm sewers, and a tank, we're still reducing the surface flooding by the same amount. However, we are now bringing the peak flows and water surface elevation in Grassy Creek back down to existing conditions. So this table shows we're slightly decreasing the peak flows with this alternative compared to existing conditions. And we're maintaining the same peak depths in the creek for that 10-year rainfall event. So the pros of storage are it helps relieve stress to the stream. So we're not increasing flows or depths. However, just note that in the way in which we're using it, it's basically taking flow off the largest storm sewer in the system in Elm Street, or basically diverting it to the tank and storing it, and we're waiting to pump it back until the levels in the creek go down. So again, because we're adding more infrastructure on, costs are increasing again. So we're going from 1.8 million up to 5.2 million. So now we want to focus on the backyard drainage because a majority of the flooding in the area is backyards. So what we looked at was, what if we address the right-of-way flooding with the new storm sewers and inlets. And then we also address backyard drainage. And in a future slide, there's a couple options for that Kathleen will talk about. But just for simplicity in the model, we're basically taking groupings of flooding in the backyards, and we're basically feeding it into the new storm sewers that we're adding. And so you can see there's a dramatic decrease in overall surface flooding in the project area. It goes from 3.28 million gallons down to 1 million gallon. But again, there's no storage in this alternative. So with all this additional flooding that we're taking from the backyards and we're getting it to the creek, you can see a huge increase in peak flow. And you'll also see an increase in water surface elevation. So we're increasing the peak flow now by 7.9%. We're increasing the max water surface elevation in Grassy Creek by 3.5 inches. However, we are reducing flood volume. So again, so this alternative was 4.6 million. So now what we wanted to do was, okay, let's address front yard flooding or right-of-way flooding, backyard flooding, but we want to include storage so we're not impacting Grassy Creek. So we looked at the new, sticker shock here. We looked at the new storm sewers and inlets in the right-of-way, the backyard drainage, and in this case, to get Grassy Creek enough storage volume to hold back flow from getting into Grassy Creek during the peak times, we had to add all 3 of those tanks that we had cited. So we are able to decrease peak flow, decrease water surface elevation, and increase flood volume by about 70% in the area. But again, comes a higher cost, $14.2 million. So the other item to consider are rain gardens. And again, rain gardens are those, grassy swale looking structures that have a media underneath the turf grass that have higher conductivity. So basically water will infiltrate faster. There's storage inside of these units, although it's not to the magnitude of underground storage. So we looked at what if we added rain gardens. And what we wanted to focus on was, based on the resident feedback, was focus on the right-of-way. And so what we did was we standardized the typical footprint of one of these units. But what we were finding is when you're looking at a 10-year rain event, there's not a lot of storage in these rain gardens. So where these rain gardens are most beneficial are to address rainfall from smaller rain events. They also are really good at water quality benefits. So if you've got a lot of debris in the streets, it's good to capture them in this, and it's filtered through the bioswale media, so you're not sending all that hydrocarbons or debris into the creek, so it helps maintain creek health. And then again, they're good for smaller rain events where you can basically hold back the peak flow and slowly feed the flow that's filtered through these units back into the storm system, so you can reduce peak flow. So they're really good at reducing peak flow, more so for smaller rain events, but in terms of the volumes and peak flows we're looking at in the creek, you would need a system-wide rain garden program to offset the need for these storage tanks just because of the volume. So, but it is good practice because they do provide water quality benefits and an attenuation of peak flow during smaller events. So again, this graph shows that with the rain gardens, we were still increasing peak flows and peak depths in Grassy Creek. So, and so just another benefit of rain gardens is, again, you can help relieve some of those red pipes where they don't have a lot of available capacity. And if you want to send additional flow to those pipes from the flooding, rain gardens will help reduce the peak in those pipes because it takes time for it to filter down through the gravel media into the under drain and back to the system. It does offer many water quality benefits. Some locations are dependent on elevations too. These are typically, 3.5, 4 feet deep overall. So you have to be able to pipe these back to the storm system. So if your existing pipes are only, say, 3.5 feet deep or so, it's gonna be very challenging to put one of these in here unless you end up going with really shallow media depths. And when you start getting lower depths, the odds of the biossoil media will start clogging over time with the particles that it's collecting, and it'll just require more maintenance and it'll cause more maintenance issues. So, there's limitations on elevations. But also good locations would be, say, upstream of, where runoff discharges into some of these street side swales, where you can, prevent some of that debris from getting in the swales and building up over time, reducing the available capacity of these swales. So then, I guess to kind of summarize the results, Kathleen will go through those.
So this is a quick summary table of pretty much everything we just talked about. So along the left side, we have the modeling scenarios that we looked at. Again, we start with the existing system as it is now, and then we kind of built the storm sewers, and then the storm sewers with underground storage, and then we had storm sewers with backyards, and then we added storm sewers, backyards, and storage, just because we're taking those stair steps. We added the storm sewers. That had impacts to the creek, you can see in the red. Then we added storage to mitigate that creek impact. Then we added the backyards in addition to that stormwater, the storm sewers in the front yards, and that had impacts to the creek. And then we added those 3 tanks to mitigate that impact to the creek. And again, you can see the costs. This is kind of a graphic to kind of show basically the same sort of thing. So you can see on the x-axis on the left, we have the percent flood reduction. Again, this is the surface flooding in the area. So we're able to get about 20%, 21% of the flooding if we do storm sewers and maybe 1 tank, and then we are also mitigating that creek impact. And then the other 2 options where we had was looking at the storm sewers and backyards, but in order to mitigate that creek impact with all that additional water from the backyards getting to the creek, then that's the $14 million price tag. And those estimated costs are shown in those yellow dots and correlate with the y-axis on the right. So this is kind of the overall summary that we have. Again, just looking at flooding addressed and the cost, and then the stress that's placed on Grassy Creek. And so basically it looks like we're pretty good on time. We just kind of ran through some of these last results slides. But one of the other things that we wanted to discuss is stream cleaning. So looking at the condition of the creek, there are areas where there's a lot of deposits and sediment that can be removed, and if we do remove that sediment, that water surface elevation would go down a bit. And same thing if we remove some of the debris that kind of holds some of the water back. If there's obstructions in the waterway, if we remove that, then that will improve and provide more positive drainage for the area. So that is also an option. Yeah.
Was all your analysis done based off of a clean creek or a creek with debris and sediment in it?
It was it was with the debris and sediment. It was basically from the survey.
Yeah, it's what the survey
You were
results.
measuring actual flow rates and actual heights.
Correct. Yeah.
Yeah.
So if we wanted to say model a scenario where you had stream cleaning or debris removal, so we could basically adjust our profiles. But the survey, they did survey the basically the top of any kind of solid debris. If there's a little bit of silt, they would stick the rod down. But
Yeah.
Did you do the analysis based off what a clean creek would?
that was yeah. So that's definitely something that we do want to run and see what the impacts are. I guess before we did that, we wanted to get feedback on that, because I know in talking with some people that opinion was expressed that it didn't seem like they wanted that to happen on their specific property. So I just wanted to get feedback and see if that's something that people living along the creek would be interested in considering.
Yeah.
But yeah, that we should run that and see what the impacts are.
I'd be curious to see
Yeah,
what that creek would flow with a clean profile.
yep.
Yeah.
Question on the storm sewers, have they considered going down between the two streets in the backyard where most of the flooding is, taking a sewer line down that way, either to this storm sewer on south boundary or to the creek to the other opposite end?
Yeah, we did, in the alternatives we did, and it was highly dependent on elevations. But there were some backyards that were routed down to south boundary. And then others that were routed into the north-south street with it going north towards Grassy Creek.
And then another option that we wanted to discuss is what could happen is if when those new storm sewers go in, an option would be to leave taps for residents to install their own backyard drainage and then connect that backyard drainage to the storm system. Obviously, the city is going to have to monitor the creek and make sure as private residents install their drainage and can make those connections to that tap, that we're monitoring the creek and make sure we're not having adverse impacts to the creek, and we can mitigate that. Okay. So before you guys leave, we want to collect, I guess we have questions for you. There's a questionnaire that Dustin has in the back, and we'll pass those out. Basically kind of going through some of the things that we discussed with storm sewers, with tanks, with debris cleaning in the creek, with whether you'd be interested in connecting to a tap if the city was to install taps in storm infrastructure, and just gauge your opinion. There's also an area at the bottom of the sheet where we can get your opinion if you have other thoughts. So please, before you leave, fill that out, and then please return them to the podium up front. So, yeah.
I have a question.
Yeah.
I live along Grassy Creek on Hickory Street. And for years, we have had cleanup as private property owners.
Okay.
It's our job to clean out the middle of the creek. And I, as a single person, do it myself. I can't really afford a professional to do it.
Yep.
But even when you do a really good job, then the minute there's like a rain event, you go down there and there's trees back where you had cleaned out. So, I mean, it would almost have to be a cleaning from, the beginning to the end of the creek.
Yeah, it would be ongoing maintenance, yes.
Yeah, it is a challenge. And it would be something where some sort of maintenance plan would have to be kind of identified, and maybe there's certain triggers that would, sign to, hey, now's a good time to do this, but it is a challenge, you know.
It's happened along, around spring brush pickup, you could then put the brush there for the city to pick up.
Yeah.
And I also had a question about, has there been any discussion about how this project is to be funded?
So,
Yeah, that's not in the scope of this report, but of course, that's a prime question that everyone wants to know. There's a lot of information in here, and of course, there's high dollar amounts. This report, once the report is finished, will go to city administration and will go to city council and be digested and then figured out what the next steps are. I know in the first meeting, I told some residents when they asked, would it be special assessment? That is a possibility, but that decision has not been made now. If the city would decide to go that or to pursue that, There would be certified mailings to every property owner. There would be public hearings. There would be opportunities to object. So I don't want anyone to leave here and think, oh, we're going to get assessed on our taxes for that. That may happen, but there's a defined process for getting to that decision.
Thank you.
I live on Walnut Street, and on the north side of the creek, they just here, last summer before last, they put in new storm sewers. They put those access taps that you were talking about on every property, but they were not allowed to tie their downspouts into it. Only their sump pumps. Well, the downspouts are part of the flooding problem. My sump, half of my backyard drains into my sump. The other half drains into my neighbor's yard. So what's the sense in putting in the taps if you can't tie into it? Where the problem is. You know, that's.
We allow nobody in the city of Perrysburg to tie their downspouts. Brand new subdivisions, old subdivisions, the same thing. You cannot tie your downspout into the storm sewer. That's consistent throughout the entire city.
The downspouts
Because-
part of the problem.
Well, one reason is because design for storm sewers, Tom made all that, it's just not, this,
It's
never
all
been
gonna
the
end
same.
up there eventually.
Eventually,
It
but it's
just,
slower
instead of
pace.
flooding my yard, it's
It's a
gonna go
slower-
to the
Right, it's
storm
a slower pace. If you want to put a catch basin in your backyard, to drain the backyard, your downspouts flow that direction, you go across the top of the grass, then that's allowed. That's how you can get rid of that water.
Yeah, the hope is
But
that,
no direct access.
yeah, the hope is that as the downspouts run over ground, there's infiltration into the groundwater table instead of it all just going
Yeah,
directly
3 or 4
there
days.
immediately. That's the
3 or
hope.
4 days.
Yeah, there's also rain barrels you can put at the end of your downspouts to hold back some of the
I
capacity.
know all the alternatives, I'm just, if you put in a tap for a storm sewer.
And as you
part of the
mentioned,
problem.
the faster the water gets to the storm system, it can be a problem, and that's why downspouts aren't allowed to be connected, because that's a very large impervious area that they're not designed to take immediately.
What's the lifespan on these storage tanks,
Um,
and where do you put them?
yeah, so
Schools are, or?
that's a good question. That's a good question. So we looked at, so there's different options for storage. You can have concrete tanks, or you can also look at, I think on one of the, you want to flip to it while I'm talking?
Yeah.
There's also options of having underground storage that also promotes infiltration. So you can try to infiltrate as much as you can while you provide storage, where they're basically like arrays of like half pipes. So the basically flow comes in and the pipes sit in gravel, and so it tries to promote infiltration on the bottom. But eventually the flow is going to get to the downstream end and pumped out. So like these right here, that's one option. The other option that we were considering, and I think the costs were based off of, were concrete tanks. As far as useful life, I guess I don't want to tell you the wrong answer, but I would assume more than 50 years. But again, I'm not.
I mean,
That would definitely be something, because part of this plan will want to, you don't just want to look at capital costs. You almost want to look at, what are, figure out what the O&M costs and life costs are, so you can develop, okay, over 30 years, this is how much it's going to cost us. So you can kind of compare alternatives, apples to apples. You can install something that's cheaper, but will it last as long? And you need to somehow normalize that so you can really truly compare costs between different alternatives. So the costs that we presented today were just straight construction costs and not factoring in any required operation and maintenance costs or life cycle costs.
And you prefer to put them in people's backyards, or where, like,
No, so-
elementary and-
No, so what we did for storage is we tried to focus on city property, so we did not look at underground storage on private property. I mean, So we tried to focus at parks for the most part. You know, if you've got like a neighborhood of backyard flooding where everybody's experiencing flooding, I mean, would one of these underground tanks work, like such as that half pipe? You know, probably, but you know, it's almost everybody would almost have to agree to that solution, and it would be more costly than piping it, you know, back to the storm sewer. So we did not include any storage on private property. Yeah.
In terms of like the gutter runoff and that type of thing, is there things we can do as like a grassroots effort? And when I mean rain gardens, I'm not talking about like the type that you're talking about, but like in our own backyards. Can't we help mitigate some of the flooding in our own particular backyard by installing a rain garden? I think I
Yes.
have stuff like a
Absolutely.
pamphlet or booklet.
Absolutely, and if
that
anyone here is
contributes to
interested,
the quality of the water, or
yes.
not as much runoff into the creek.
Yes, every house and business that has any impervious surface where water can't infiltrate into the ground, whether that's pavement, a roof, anything like that, there are things you can do in your own home, whether it's rain barrels and rainwater harvesting or rain gardens on your own property. And if anyone here is even slightly interested in that, please contact me. I would be happy to help you out on your own private property, give you guidance on how you can do that. Just come see me after.
Okay, well,
What's the depth of the water table? How far down do you get water?
In this area,
I don't know. off the top of my
I don't
head.
know the exact. I mean, it's going to depend where you are, but I would say it's probably not very deep.
About the river depth.
Yeah, you're right near the river, so.
Well, we'll be around, so if you have any questions, again, please fill out the surveys, and I know that a couple people came in late. If you came in late, please sign in, there's a sign-in sheet, a yellow notepad at the table in the back. Please sign in, and again, if you have any questions, let me know. Oh, there are extra pens in the back on the table too, if you need one of those to fill out your survey. Thank you.